Yeah, we're not.
These, what I'm passing out right now, these are just more practice problems, verifying identities and solving equations. I'm also going to write up worked out solutions for these practice problems too, so everybody can kind of see their work, check their work. So which numbers would people like to maybe go over from the homework? 52. 52? Seems like there's consensus on 52. Someone have it with them so I can write it down. So this says to solve 35 cosine squared x plus cosine x equals 1 plus 5 sine squared x on the interval from 0 to pi. Is that correct?
Yeah.
Okay, thanks, Martin. Yeah. Okay, so we'll go through this one and then maybe do a few extra examples before I start something new. I do have to get something new started today, but I think I only maybe need half of class at least. I need to finish section 6.2 by Monday just to keep on schedule with everything. The only thing I can really do, I have 2 review days set before exam 3. Exam 3 is going to cover chapters 6 and 7. And that's going to be all the material as well that the final will cover is just through chapter 7. So exam 3 will cover chapter 6, 7. There's 2 days of review scheduled before that exam. And then there will be 2 days of review set aside for the final as well. So at most I can really lose a day to keep a review day before exam 3. Okay, but right now I'm on schedule, I'm on track. We can slow down just a little bit today. Okay, so anybody have any ideas or any initial thoughts on this problem?
Sorry.
So you've got, I don't know, there's 2 terms on the left, 2 terms on the right. On the left side you've got a cosine squared and a cosine, and on the right side you've got a sine squared. Now with these, when you're solving the trig equations, one general practice is to try and rewrite the equation so that only one trig function appears. Okay, so since we already have 2 cosine terms, it'd probably be easiest to use an identity to get rid of this sine squared. Now, I recommend, if I look at the identity that we're going to use, okay, since I'm trying to replace sine squared with something, there's only one identity that has sine squared in it, and that's the Pythagorean identity. And if you solve for sine squared, it ends up being 1 minus cosine squared of x. Okay, so that's the one we're going to use. And you might as well just get used to this because as written, the Pythagorean identity isn't necessarily as helpful as solving for sine squared or cosine squared. You know, on other problems, you might have to use the fact that cosine squared is 1 minus sine squared. Okay, so really we're using this identity, but we're either solving for sine squared or cosine squared. And then what we're going to do is we're going to replace just that sine squared right there. Okay, so now what the equation becomes, you don't do anything to the left-hand side. Okay. And remember, this is an equation we're solving, right? We're not verifying an identity. This expression will only be true for certain values of x. And then the right-hand side becomes 1 plus 5, And then you need to introduce parentheses. Anytime you take a term and replace it with something with more than one term, you need to introduce some parentheses, and the sine squared becomes a 1 minus cosine squared x. Okay. And this is going to become essentially a quadratic equation where we're treating cosine x as the variable. So what we're going to do is we're going to get all terms on the left-hand side get a 0 on the right-hand side. So before we can get a 0 on the right, we have to simplify, distribute that 5 through both those terms. So 5 times 1 gives me a positive 5. And then, so what we're doing here is we're distributing the 5. 5 times 1 is positive 5. 5 times minus cosine squared is a minus 5 cosine squared x. Okay, everybody okay so far? Okay. So again, my first goal is just to only have cosines appear in this equation. And then now what I can do is I can move everything to the left, so I can add 5 cosine squared to this 35 cosine squared to get a 40 cosine squared x. I still have the plus cosine of x. And then 1 plus 5 gives me 6. That can be subtracted to the left. So you end up with 40 cosine squared plus cosine minus 6 equals 0. Okay, so that's the first part. Now I have this as a quadratic in terms of cosine of x. I don't know if this is necessarily helpful, but remember cosine squared of x, that was just a special notation for, right, taking cosine of x and then squaring that quantity. And then this looks really close to a quadratic. Normally you'd have like 40x squared plus x minus 6 equals 0. But I'm going to treat cosine of x as the variable. And I don't think this is going to, had anybody gotten this to this point at least? I don't know if this really factors very nicely at all. Had anybody tried it? Okay, so whenever a quadratic doesn't factor, you always use the quadratic formula. And like I said, you're treating cosine of x as the variable. So you can use the quadratic formula to solve for cosine of x. Okay, 40 is the A, positive 1 is B, and the negative 6 is C. And what the quadratic formula says is you take minus B plus or minus. So my B was 1, so I did negative 1 plus or minus. And then it's a square root of B squared minus 4 times A, which is 40, times C, which is negative 6. And then you divide that all by 2 times A. So I get 2 times 40. So certainly for this section, you might want to review the quadratic formula. Okay. And I know it's a little bit strange. This is a quadratic. This is a quadratic equation where I'm really treating cosine of x as the variable, and I can still use the quadratic formula to solve for cosine of x. Okay. And then let's see. I don't know if anybody's simplified this yet. Minus 1 plus or minus. You're going to get an 80 in the denominator. And then 4 times 40 is 160. 160 times 6 is 960. 960 plus 1. I believe you should get a square root of 961. Okay. Okay, so that's what cosine of x equals. And remember, plus or minus is just notation for 2 separate solutions, right? So what we can do now is we can split this up. Cosine of x either equals minus 1 plus the square root of 961 over 80, or cosine of x equals negative 1 minus the square root of 961 over 80.
So that simplifies. Do we want to simplify? The 31
Is that is the square root of this
yeah,
31?
perfect square.
Oh, even better. Yeah, let's simplify each of these.
31.
You said it's 31? So negative 1 plus 31 is going to give you 30 over 80,
Which is 3/8.
which I guess we can write as 3/8. And then over here, cosine of x, negative 1 minus 31 is going to give us a negative 32 over 80. Or if you like,
2/5.
is it minus 2/5? So 16 goes into 32 twice, and 16 goes into 85 times.
But negative 2/5 isn't in our 0 to pi.
Now, you're right. Negative 2/5 is not in the interval from 0 to pi. But when you say you're solving an equation, you're solving for x. So we're trying to find the x values that solve that equation, and those x values have to be between 0 and pi.
So is that just our final answer then, those two?
This is an intermediate step. So we're not 100% done yet. I have to solve both of those equations for x. Okay? So before I can even solve for x, I had to solve for cosine of x using quadratic formula. And then that'll split off into two equations. And are these special values that you get from special angles? No. So this time we're going to actually have to use the arc cosine function to get our solutions. So over here, x will be arc cosine of 3/8. And over here, x will equal arc cosine of negative 2/5. And I don't know if someone can make sure your calculator's in radian mode, because this interval is, we're looking for angles between 0 and pi that satisfy this equation. And then if someone gets something, maybe do a couple decimal places, let me know.
1.19.
So that's for the arc cosine 3/8.
Yeah.
1.19. 1.98. Okay. And then remember, 0 to pi is 0 to approximately 3.14. So we're looking for all solutions from 0 to 3.14. Okay, so there's two of them. Those are certainly between 0 and 3.14. And then what else would I have to do to maybe check if there was more solutions? So not pi over 2. What?
Just pi.
Okay, pi wouldn't necessarily work either. So what's the period of cosine? What can you add to an angle to get the same value for cosine? Can you say that, Janae?
It's 2 pi.
2 pi. Okay. So, but what happens if you add or subtract to any multiple of 2 pi from this? You're going to be outside of the interval from 0 to 3.14. Right, if I add 2 pi, 6.28, or subtract 6.28, we're too small or too large. And would the same be true here? If I either add 2 pi or subtract 2 pi, so there are no more, exactly. So these are, so first of all, these are the solutions exactly, the arc cosine 3/8 and the arc cosine negative 2/5. Those are technically your two approximate solutions. Okay, so a lot of these equations, your goal is to write it as a quadratic in terms of sine, cosine, or tangent. Use the quadratic formula to solve for the trig function, sine, cosine, or tangent. Okay. And then usually you'll get two, so cosine will either, well, the plus sign will give you one value for cosine, the minus will give you another value for cosine, and then we're really solving for x here. Okay, so once I have cosine of x equals something, if this would have been like a 1/2, then I would know that x would have been, say, pi over 3. Okay, so if either of these were special values that come from special angles, you shouldn't need a calculator. You should be able to find the solutions just knowing what the special light's kind of freaking out back there, isn't it? But yeah, if those were special values, you should know what the angles are without using a calculator. But because 3/8 and negative 2/5 are not special values coming from special angles, you can use arc cosine to get your x. Okay, and then on the practice problem sheet I passed out, Number 8 and 9, you'll have to do a similar type of thing where it'll reduce to some quadratic equation, and then you can use the quadratic formula, or you can factor. 7, 7 just comes down to factoring. You shouldn't have to use any quadratic formula in problem number 7 on my practice problems. But 8 and 9, you'll have to do a similar type of strategy. And like I said, I'll try and get solutions to these practice problems posted today. Otherwise, maybe, I don't know, I'm leaving for that conference at like 3 o'clock today, so it might be hard. You know, maybe one thing I could do is I could write the solutions. I could take a picture with my cell phone. I'll see if I could email that to myself somehow and email it to all of you over the weekend. But for sure, I can have this to everybody by, I'll try and get it to you this weekend somehow while I'm at this conference. I'm sure I can find a printer somehow. Okay. And then for the quiz, I decided again just to give people some extra time just to think about these. They take a while to get used to, especially verifying identities. Right? Solving equations, there's an answer. The identities are kind of funny, right? You already have the answer. You need to show why it's true. It's kind of like a mini proof. Okay? So those are strange, right? It's a math problem that doesn't have an answer. Right? Something that you have to show using your identities. So everybody, is there any other ones from the homework, or anybody maybe want to do a couple off these practice problems? Janae?
Actually, for like 38, I know it's like one of the easier ones, but I keep confusing myself. I've got to like a point where I can't really solve it anymore, and I don't know how to go back and like fix it.
Okay.
I keep straying further and further.
Were you in class on Tuesday? Okay. I think we did 38.
I think it was
No, we did 48.
We did 48? Okay. So let's at least look at that then quick. Like I said, I just need maybe 25 minutes, so I can take 10 more minutes before I have to start something new. Was 38 an equation or a verify one?
Verify.
Okay. Someone want to maybe remind me what it was?
Cosine x.
Hold on. So cosine of x,
Cosine of negative x. They're multiplied together.
cosine of minus x.
Plus sine x. Times sine
Oh,
negative x.
I remember this one.
Equals 2 cosine squared.
Okay.
X minus 1.
Just like that?
Yeah.
Okay. So Janae, what do you have so far? So which side did you start with if you were gonna?
With the left side.
I think that's a good idea. I think the left side looks a little bit more complicated. And over here you just have an input x. You'd have to somehow like change it or introduce a minus x somewhere. So we'll start with the left-hand side. So again, we start with the left-hand side and simplify into the right-hand side. So pick a side you want to work with. If you get stuck, sometimes what you can do is you can start maybe trying to simplify the other side to maybe try and meet somewhere in the middle. But all of these can be done by just picking one side and simplifying into the other. Okay, so you took the left. And we're going to try and simplify that into the right-hand side. So any identities you tried to use right away?
I pulled the negative out of the x, because
Okay.
I know the quotient things, but like it would just still be.
So
a
by
problem.
name, you're
Even
using
odd.
the even and odd identity. And we know that cosine of minus x is cosine of x. If you look at the graph, it's symmetric about the y-axis.
Mhm.
It's an even function. And sine is an odd function. Sine of minus x equals minus sine of x. Okay, so over here, this can just be replaced with x, right?
Mhm.
So you'll get cosine times cosine, which will give you a cosine squared. So I skipped a step there. Cosine of minus x is cosine of x. Cosine of x times cosine of x is cosine squared. Over here, I'll be a little bit more careful. You said here you took out the negative sign? Okay. For now, I'll just do this. Okay. I'll rewrite sine of minus x as minus sine of x. Okay, so I use my even odd identities first. And then what's sine of x times minus sine of x? That's going to be a negative sine squared x. Okay. Now, where are we trying to go? Sometimes it's good to stop and say, okay, what am I trying to get to? You're trying to get to an expression involving cosine squared. So you probably want to keep this term, right? But you need to somehow rewrite the second term. Okay, and then remember, using the Pythagorean identity, sine squared of x is really 1 minus cosine squared. I start with sine squared plus cosine squared equals 1 and subtract cosine squared on both sides. Okay, so now what you can do, this will equal cosine squared of x minus. Now what do you have to be careful about again if you take a single term and replace it with two terms? You need to make sure you replace what you're introducing with parentheses. Okay, so the sine squared became a 1 minus cosine squared, and because we introduced two terms, we need to enclose in parentheses. And where were you stuck at, Janae? Were you maybe at this point or kind of somewhere over here?
Yeah.
Okay. And then what's my next move? Okay, we'll distribute that negative or that minus sign. And you'll get cosine squared x minus 1 minus a negative cosine squared, which becomes a plus cosine squared. And is that going to do it for us? Yeah, because cosine squared plus cosine squared gives us two of them. And then you still have the minus 1. And that verifies the identity. Yeah, Martin.
Would you have been able to do the right hand side? And that's what I did, and I don't even know if I did it right.
My thing is, I get you can always start with the right hand side, but then I guess you'd have to be really tricky, right? 2 cosine squared you'd have to write as, I guess you can just go backwards, right? If I wanted to start with the right-hand side, these would be the steps I would have to do. But I think, so yeah, you could certainly write 2 cosine squareds as a cosine plus a cosine. You'd have to know to factor the negative out of these two terms. You'd have to know to replace this with sine squared. You'd have to know to rewrite this as cosine times cosine plus sine times minus sine, and then you'd have to know how to use your identities to replace x. I just think that side's more difficult. So you can do it, but generally I like to start with the side where it's easy to see which identities to use. If you start with the right-hand side, you got to be much more clever than if you start with the left-hand side. And then anybody want to maybe just do one more from these practice problems? I think we have time for one. How about number 6? So this is number 6 from the practice problems. Okay. And then like I said, we're probably going to do the quiz on Monday. If I don't get the solutions to you, then I'll probably do the quiz on Tuesday. Okay, so just keep checking your Canvas over the weekend. If I post the solutions to all of these, we'll probably have the quiz Monday. If I don't get these out to everyone, we'll just do the quiz on Tuesday. Alright, so number 6 says verify secant theta equals sine theta tangent theta plus cotangent theta. Okay. Now, I think it's pretty easy to see which side's more complicated this time, right? This left side's just a single term. And if I start with the left-hand side, I'd have to be pretty how do you say that? You'd have to be pretty clever to introduce a bunch of terms to get to the right. So I think it's a lot easier here, again, this time to start with the right-hand side and simplify into the left-hand side. Okay, so I'll start with the sine theta, tangent theta, plus cotangent theta. Okay. Now, there's no negative angles, right? So there's no need to use any even-odd identities. Is anything being squared? No. So the Pythagorean identities probably aren't very helpful. Anybody maybe see any identities from that 6.1 worksheet that might work? Okay, so Kirsten's recommendation was maybe the only thing we can do here is use the, what were they, the quotient identities?
Yeah.
We can rewrite tangent theta and cotangent theta. So this would be sine theta, tangent is sine theta over cosine theta, and cotangent is just the reciprocal cosine theta over sine theta.
And then distribute the sine.
Yeah, let me see. Do I want to do the distributing the sine?
Yeah.
Sine squared over cosine theta. Okay, let's go with it. Okay, it wasn't what I was going to do, but let's see if it works. All right, there might be a few different ways you can do the simplifying to get where you want to go. So I'm going to go with Kirsten's suggestion. We'll distribute the sine theta and see if it works. So for the first one, sine times sine, you're going to get sine squared theta over cosine theta. Remember, we're ultimately trying to get to secant theta. And then it's going to be plus sine times cosine over sine. The sines are going to cancel and leave us with cosine theta.
Then you use the Pythagorean, I can't say the word, theorem of
The Pythagorean theorem?
I can't say that.
It's okay, I can't say it. Ingenuity, ingenious. Okay. So you're saying use the...
Yes.
So actually now I see three ways to do this because I saw a particular way to do this that is different from what you said. Okay, what I was going to think was get a common denominator. Right? Because then I'd get cosine squared over cosine, and when you add sine squared to cosine squared, you'll get 1. Okay, however, your way will work too. So I'm actually going to kind of split into two roads here, because I just want to show you that there isn't just one way to work these down, right? What Kirsten might think of, what I might think of, what someone else might think of, they might all work. Okay, so I'll go with Kirsten's first, because I think what you're saying is you can write the sine squared as 1 minus cosine squared.
Yeah. Bless you.
Bless you. And then where were you going to go from there?
Well, then I separated the 1 cosine minus cosine squared over cosine.
Okay,
and
so you
separated
split
them.
this into two separate fractions.
Yeah, and then you'll get 1 cosine theta minus cosine squared over cosine plus cosine, and then the cosine squared will cancel out, so it'll be negative cosine plus cosine, so then all you have left is the 1 over cosine theta, which is secant theta.
Perfect. Okay, is it okay if I repeat that to everyone?
Yes.
Okay, so what she said was this cosine squared over cosine just becomes cosine, minus cosine plus cosine, those two terms will cancel, and then 1 over cosine is secant theta. So there'd be one way. And then what I was thinking was actually to get the common denominator. Hold on, I'll give you a second to catch up. Yeah, you'll get, if you get the common denominator, you'll multiply this by cosine over cosine to give you cosine squared theta over cosine. And then if you add those, you can add those two together because they have a common denominator. You get sine squared theta plus cosine squared theta over cosine. But what's that sine squared plus cosine in the numerator?
1.
That's 1, and 1 over cosine is secant theta.
I think this is why this is so hard, is because there's so many ways to do it. We feel so unsure when we
Yeah,
try
it is very uncomfortable at first. That's part of math, is just kind of getting comfortable with being uncomfortable. I know that's kind of a weird statement, but it's okay to not know what to do. I mean, you just got to keep trying things until something goes your way. And then the more and more you practice, the more and more you'll get better at seeing where you're going and what you try, where it's going to lead you. But again, if you don't do that practice, you're not going to really have any idea what to do. Okay? So I'll try and, like I said, I'll all the rest of these practice problems, I'll try and get those worked out and sent or posted on Canvas over the weekend. If I don't get them posted until Monday, we'll do the quiz on Tuesday. Okay. All right. I think we'll get better as we do this, because the next two sections are just more identities. Okay, there's like sum of angles to products and product to sum and double angle formulas. So we're going to get some new identities, but I think you'll get better and better at kind of seeing how to play this game, as I call it. Okay, so let me, like I said, I know that it'd be great to have all this time and spend more and more time on this, but I'm kind of bounded by getting through our curriculum and making sure everybody sees what they need to go into the next class. Okay, so today we're going to learn sum, difference, and double angle identities. Okay, and we're going to first do the sum and difference identities. Now, if you want to, you can read in the book. There's some pictures. There's an interactive figure that kind of explains where these identities come from. Although, I don't think it's worth spending the time on it in class. I don't think that where these formulas come from are very instructive. I don't think we'll learn much from where they come from. Okay, so I'm just going to give you the identities. If you're interested in where they come from, you can always talk to me outside of class. You can try reading in the book and read their explanation for why these identities are true. Some of our other identities were a lot easier to see, like the Pythagorean identity just comes from the Pythagorean theorem. Yeah?
Didn't you say you were going to have extra office hours today?
I was going to have extra office hours today, but because I'm getting a ride to the conference and they're leaving at 3 o'clock, I can really only hold my regular office hour till 2:20. I'll do some extra hours next week when I get back, so I apologize for that. It's just that my ride is leaving early, so I can't stick around longer today. I'll be available after class, though. I'll be down in my office right after class, so I guess I can donate that hour to everybody too. Okay, so let's just write these down first. This is also a good point to maybe start writing some of these down. I'm not going to give you any formulas for the quiz on Monday or Tuesday. I don't think there's really that many identities yet, but since there's going to be more and more coming, I will print off some sort of sheet for everybody that's got the ones you need to know and the ones that I'm going to give you for free. Okay, so you won't have to memorize all of the identities. But certainly for the quiz, I want you to remember the basic ones. The quotient identities, even-odd identities, complementary angle identities. Those are the ones like cosine pi over 2 minus theta is sine theta. Okay, so I think it's okay to have everyone learn those ones. Okay, so some difference identities. And the main ones here, these are the fundamental ones. So the fundamental ones are in the box. And the reason these two are boxed is that the other ones can be derived from these two. That's why they're called fundamental. So first of all, we can look at the difference. So cosine of a difference of angles. You do cosine of the first, cosine of the second, multiply, and then you add sine of alpha times sine of beta. So that's the difference identity for cosine. And then there's a difference identity for sine. So this one, you start by doing sine alpha, and then you do cosine of the other angle beta, and then here's, oh, no, I got it right. And then here's one thing I remember, since I'm doing this for sine, the sign stays the same. Okay, so it's going to be a minus sign, and then you just do it in the other order. You're going to do cosine alpha, sine beta. Okay. These ones aren't as important to remember, so on the test there's probably a good chance that these are ones that I'll be giving you for free. Okay. They do come up in calculus classes, you use them in other math classes, but you use them like very little in isolated places, so usually your teacher will just give them to you if you need them in those classes. If they don't, they're jerks. You can tell them I said so. Okay. And then I could do this one too. If I wanted to do tangent alpha minus beta, what would I do? I would just do sine alpha minus beta over cosine alpha minus beta. And when you simplify, so if I actually did the sine over cosine, you end up getting tangent alpha minus tangent beta over 1 plus tan alpha tan beta. And then the other ones are pretty easy to remember. So here's the trick. If it was cosine alpha plus beta, the only thing that's going to change is, anybody have a guess? Well, if that's a minus and this is a plus and I switch the signs, it's just going to be the same thing, but the right hand side is going to be a minus. Okay. And then, let's see. I think this comes from just doing cosine of alpha minus negative beta. And when you plug negative beta in on the right, or sorry, if I was over here, if I plugged the minus beta in, the minus sign would just come and change this to a minus. Okay, so this identity is just gotten from this identity by replacing beta with minus beta everywhere you see, and then simplifying. And then sine alpha plus beta, again, the way I remember this is it's sine of the first, cosine of the second. The sign stays the same, and then you do it the other way. You do cosine the first, sine of the second. And then finally, tangent alpha plus beta. It's the same thing as on the left, but this minus, you just change the signs on top and bottom. That becomes a plus, that becomes a minus. So tan alpha minus tan beta over 1 plus tan alpha tan beta. Okay. So for this section, there's still going to be verifying identities. There's still going to be solving equations using the identities, but there's one extra piece, and that's what we're going to do in this first example. So I think since maybe I'll come over here and do this example. So example 1, we're going to use the fact that 1/12 is 1/3 minus 1/4 to evaluate, and I think I have sine 5 pi over 12 and cosine 5 pi over 12. Okay. Now first off, does everybody buy that 1/3 minus 3/4? If you get a common denominator, you're going to get 12. This 4 is just going to come up here, and this 3 is going to come up there. 4 minus 3 is giving me the 1. So if you get a common denominator and simplify, 1/3 minus 1/4 is 1/12. Okay, so interestingly, what these identities are for, they allow you to find the exact values at other angles besides our special angles, right? Our special angles are what? 0, pi over 6, pi over 4, pi over 3, pi over 2. And by rewriting 1/12 as 1/3 minus 1/4, we'll be able to use the sum and difference identities and then use what we know about the special angles, and we'll be able to do this without a calculator. Okay, so for instance, if I do the sine 5 pi over 12, this is the same as sine of 5 pi times 1/12. So I'm pulling the 1/12 fraction out, multiplying. This would be the same as sine 5 pi times 1/3 minus 1/4. And then finally, if you distribute the 5 pi, you get sine 5 pi over 3 minus 5 pi over 4. And those are both special angles. So 5 pi over 3 and 5 pi over 4, those were both special angles on the unit circle. Okay. So far we haven't really done any pre-calculus. I just did arithmetic. Right? 5 pi over 12 is the same as 5 pi over 3 minus 5 pi over 4, because 1/12 is 1/3 minus 1/4. I guess I could have made this easier too, right? I could have just multiplied by 5 pi on both sides up here. Alright, so I want to leave these two identities up for now. This will now equal, so first of all we're doing a difference of angles. So what's going to be your alpha and what's going to be your beta? So what's the first angle appearing? This 5 pi over 3 is going to be the alpha. The 5 pi over 4 is the beta. Okay. So when I apply the property, it's going to be, so you do sine of the first times cosine of the second. So you'll do sine 5 pi over 3 cosine 5 pi over 4. And then the thing that you remember with sine is that the sign in the middle is the same as the sign in the middle on the right, minus, and then you just do it the other way around. You do cosine of alpha, or the first angle, times sine of the second angle. So right, this is alpha beta, alpha beta. That's a bad alpha. And then let's just come off to the side and do these for now. So we got to find sine 5 pi over 3. We got to find cosine 5 pi over 4. We got to find cosine 5 pi over 3 and sine 5 pi over 4. And you know what? I'm going to do this with reference angles. And then thinking about which quadrant these angles are in. I think 5 pi over 4 is in the third quadrant. So maybe it would be helpful if I draw the unit circle here. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So there's 5 pi over 4. And then we can look at where 5 pi over 3 is. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3 is going to be down here. Okay. And then we can, I guess, do reference angles, because this is now going to be pi over 3. The reference angle over here is going to be pi over 4. Okay, so sine 5 pi over 3, sine is negative if you're in the fourth quadrant. So using reference angles, this is the same as minus sine pi over 3, and sine pi over 3 is root 3 over 2. Cosine 5 pi over 4 is cosine positive or negative for an angle in the third quadrant? Negative. So this will be minus cosine of the reference angle. That'll give you a minus 1 over root 2. Cosine 5 pi over 3. If you're in the if an angle's in the fourth quadrant, is cosine positive or negative? Positive. So this will just be the same as cosine of the positive cosine of the reference angle. Cosine pi over 3 is 1/2. And then sine 5 pi over 4 is sine positive or negative in the third quadrant. Negative, right? Sine's the y coordinate. We're below the x-axis. This will be minus sine of the reference angle, which will be minus 1 over root 2. Okay. And then now I just plug and chug. So I'll plug all these values in down here and we'll simplify. So what do you get? Sine of 5 pi over 3 was minus root 3 over 2 times cosine 5 pi over 4 is minus 1 over root 2. Then you have a minus. Cosine 5 pi over 3 was 1/2 times sine of 5 pi over 4, which was minus 1 over root 2. Okay. And then now we can just multiply each of these fractions on the left. You get root 3 over 2 root 2. The sign is going to change to a positive. This negative comes out front and makes that a positive. And you'll get 1 over 2 root 2. So when you're done, it's root 3 plus 1 over 2 root 2. And that's sine of 5 pi over 12. A lot of work. However, it's good review for previous sections, right? It gives you good review on your reference angles from 5-2, in your unit circle. You're knowing your values of the trig functions for special angles.
Really quick, what
Yeah.
is that 1/2 and that one square root 2 over square root 2?
Where at? Right here?
No, the other one. No, the 1/2.
I just replaced cosine 5 pi over 3 with 1/2, so it went here.
Yeah.
So why is cosine 5 pi over 3 1/2?
Oh no, I see what you're doing.
Ah, okay. Depending on how you write these, your answer on the right might look different. Like some of you, I think, like to use square root of 2 over 2, right? So you'll get something that looks different, but it'll be an equivalent answer. And I don't care if you rationalize the denominators or not. Okay. So this would be a final answer, right? And then we already did a lot of the hard work for, right, if I want to do the cosine 5 pi over 12, all these same values are going to show up again. Okay, so we already did a lot of the hard work. Okay, is everybody okay if I just erase these circles up here? Okay. Let me just wait another 30 seconds here, a couple seconds to let people get caught up. Okay. Now for this one, we already simplified the 5 pi over 12 as 5 pi over 3 minus 5 pi over 4. So we'll start with that. Let's see if I even remember how to do this. So it's going to be cosine of the first angle times cosine of the second angle. And then what happens to the sign when you're doing a sum or difference for cosine? If you start with a minus sign, the right-hand side is actually going to have a plus. And then you do sine 5 pi over 3 times sine 5 pi over 4. So that was using my difference identity for cosine. So cosine of a difference of angles is the product of the cosine of both angles plus the product of sine of both angles. And then I think now you can just plug and chug. Cosine 5 pi over 3 was 1/2. Cosine 5 pi over 4 was minus 1 over root 2. plus the sine of 5 pi over 3 was minus root 3 over 2. Sine of 5 pi over 4 was minus 1 over root 2. And then are both terms going to have the same denominator? I guess you're going to get minus 1 over 2 root 2 plus root 3 over 2 root 2. And it's pretty close. It's not exactly the same. Ends up being root 3 minus 1 over 2 root 2 when I add those together.